Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad you've taken the time to join us today as we look at our topic of how to ensure screws are tightened in the correct fastening sequence. And so this all kind of flows with what we presented last month in regards to error proofing. So this kind of goes hand in hand with that. The whole idea behind error proofing is to kind of craft behavior for the operator to give them the opportunity not to be able to make a mistake. And so that's kind of what the whole process behind sequence control is, with allowing the operator to not have the ability to make a mistake. And when we look at some of the things that we want to try to achieve with that, we want to make sure that we can get it right the first time, that we're preventing mistakes from happening. And if there is a mistake, how can we manage that and correct it right away? This all falls under the umbrella term of poke-yoke, if you're familiar with that from the Toyota production systems. But within this error proofing concept, if we can do that, then we are looking at a way that we can control defects from leaving an operation. When we look at sequence tightening and some of the failures that can go along with that, the whole idea behind doing a sequence is usually to make sure that the part or the flange or a board, whatever it is that we're tightening, gets seated correctly. So it's not tilted up on one side or we're not getting a good seal because there's a gasket that we're trying to compress and we're trying to compress it evenly. And so these are some of the challenges that persist with a sequence and its tightening failures that go along with that. And so that'll kind of jump us right into our poll question for today. This is a pretty simple question that we're looking at, and it is: do you have any tightening sequences in your particular operation? So if we can go ahead and we can launch that, we'll see what our results here real quick, and then we'll move on with the presentation. All right. Thank you for participating in that. In our answers, it looks like the majority is that there are sequences that do need to be looked at, or there is a combination of tightening sequences and non-tightening sequences, and some just had neither, but the majority was that there are sequence fastening processes, which is great because that's kind of what we're looking at here today. So anyway, whenever we talk about our challenges that relate to fastening, there are certain common ones that we always typically seem to highlight, and those can be from fasteners that get over torqued, if we're dealing with maybe hand tools, or we get fasteners that are under torqued. In both of those situations, any type of vibration or shock can cause failure to that particular part. So if we can make sure that things are tightened correctly, we have a better chance of making sure that the assembly doesn't fail. There can also be things like the human error that plays a part in operators not paying attention. It could be that production is calling for things to get done quickly, and so operators are rushing through different processes. Some fasteners don't fully get torqued and the heads are lifted, not with any torque value on them at all. And so there are a number of these challenges that can result in errors. And so, how can we safeguard against sequence and tightening failures? Well, the first thing is that if we can go ahead and introduce tools that are equipped with the error proofing capabilities that can help us track the sequence of each fastener, and that's going to help monitor the fastening process and ensure that every screw gets tightened correctly, and not only gets seated or tightened, that they all get done correctly. And if there is an error, we can detect what that error is. We can go ahead and make the adjustment and get that handled right when it happens, so we don't have to come back and spend time and money or resources in rework. And so we did touch on some of the human errors that may be typical within some of the common fastening errors. And just to highlight a couple more, we're looking at maybe operators that fully don't understand the assembly and why it's important to have a sequence. And we all know that the assemblers, they have a better idea of how things should be done than what we're trying to get them to do. But that's another discussion. We also have maybe a lack of experience or training for the operator. Maybe they misidentify certain parts and procedures because there may be a mix that happens and the operator uses the wrong fastener or grabs the wrong component to be used. And there may be inadvertent errors that the operator is just simply not paying attention, thinking about what's happening this weekend or what's coming up. And so they're really not invested into what they're doing. And so those are some of the items that deal with the operator, but there also could be lack of supervision or oversight, making sure that they are doing those things correctly. Now, with a position control system, this does allow us to be able to have all of these things that we're highlighting that potentially could be an error, how we can solve for this in an assembly process. And so, position control system basically is an all-in-one torque control arm that corresponds with a display that allows us to walk through a certain assembly in or allow us to be able to direct and guide the operator through the assembly properly. And so the first component is going to be the torque arm. In this position or this picture here, we're looking at the articulated torque arm, and with this, there are two optical encoders that read at the one joint and again at the top, and this helps us to monitor the tool where it is in space. And so we have the ability to know exactly where the tool is, and we can account for where that is. Now, there are other options as it relates to the arms. Now, there is a linear style torque arm, which allows us to monitor the tool's position forward and back, and then we could also monitor the rotation that happens as well. And then for those types of applications where we may need a little more flexibility, we do have telescoping arms that can monitor a number of different things. So we can have an arm that monitors the actual length that's happening. We can monitor the amount of angle that happens. We can also monitor the amount of turn that may happen within the tool itself. So depending on the application, you may need just one of those three, or it could be a combination of all three in one particular arm, depending again on the application. And the telescoping arm does give you the ability to move the tool out, rotate it. So if you do have some of those applications that require more adjustment to the tool, than what we're showing today in more of a vertical position. There are those options that are available. The other benefit to using an arm is there certainly are going to be ergonomic benefits to that. We help to eliminate any type of stress on the operator, either as it relates to holding the tool or using it within a balancer. We can also provide protection against any type of repetitive motion injuries, such as carpal tunnel. And you'll see this typically more in higher torque values, things that are up over 20 inch-pounds or so. But it's also really critical if you are dealing with a low torque application to have the tool in an arm. This also prevents the operator from adding any additional side load or inadvertent torque to the actual assembly, because we're keeping the tool in a controlled device. And that's kind of what we're showing today with our new MD Mini torque driver. In fact, the tool that I'll be using in this demonstration has a torque value that's just under 2 inch ounces up to about 9 inch ounces. So really, really low in the torque value. But again, it's really beneficial when we have that in a torque arm. Now, the controller or the touch screen, which is the DPC Touch, that communicates and controls the arm, acts kind of like a mini PLC, where it can direct the operator through the actual process. There are 12 digital inputs and outputs that can be used to integrate it with buttons and switches. Could be Pictolite sensors. You can also have this connected to a pneumatic lock, certain things like that. But this basically controls the operation. It is Industry 4.0 ready, and this is what's going to help us ensure the actual sequence process with that, because the way that this system functions is it is based on a certain step, and the operator can't move on to the next operation until that certain step is complete. And this is very helpful in a fastening operation, because we're only going to allow power to be to the tool when it is in the right location. So there's not going to be the ability for the operator to tighten any other fastener but the one that they need to tighten. And it won't allow the operator to move on until that one has been done correctly. So, we talk about sequence-based fastening, and we understand that in order for many operations to seat something correctly, it may take multiple passes. We may be dealing again with a flange or a gasket, but this system allows us to be able to do that sequence-based tightening very, very easily. It also is going to allow us to monitor the screw count through a job manager, and that job manager can hold hundreds of different jobs that may be presented to the operator if we're dealing with maybe a low volume, high mix type of operation. And those different jobs and programs can be selected either by a simple barcode scan, or they could be selected by, again, a PLC or any other type of input that may be able to identify that particular part. But we can do all of that with the actual controller. And it's really pretty easy for us to be able to do the sequence and go ahead and create that. And that's kind of what we're going to look at today through our demonstration. We're going to go ahead and we'll create a sequence pattern from kind of basic start to finish, and that can give you a really good idea of how we can go ahead and use the DPC touch along with the position control torque arm. So let's go ahead and jump into our demo. And what we have here today is we have our MDC mini controller. This is going to tell us here which preset we are using. It is going to tell us our unit of measurement, which currently we're in inch ounces. Shows us what our last torque value was here. We have our target torque for this preset at 4.25. But we are using preset 1 a little bit differently, and we'll talk about that as we move forward. Here is the DPC touch controller, and then we do have our torque arm with its encoders that is going to be reading the position of the tool, and we can go ahead and see that here in just a minute. We also have our thread block here of our M2 fasteners along with our MD Mini, and you can see that here. Here's our MD Mini in our torque arm. And so what is our first step is we'll go ahead and we'll jump into the DPC touch. We're going to create our multiple step fastening for our fasteners here, and they're just in here right now just to make the demonstration a little bit quicker. And so let's go ahead and jump into the touch, and this will allow us to go ahead and set up our program. So in our job manager, we can go in and can select. We have different jobs in here as well, but let's go ahead and go to our webinar, and we'll go ahead and edit this. And for some simplicity, we do have our fastening step here, and it is out of the different steps that we have available. Let's go ahead and edit this. Now, I only have one fastener saved in here right now, and what you're looking at here is the channel values for the encoder. And so if I move the arm, you can see that those values change. And then we have our tolerance settings over here that will allow us to make sure that we're in position with our target. And if we are, then we'll get the ability for the tool to be unlocked and ready to be used. But with that, first, let's go ahead and set up our torquing pattern. And so if I select the image, so here is the image of our thread block, and we only have one position in here for our fastening. And so this is position 1 here, and we can come back out, and we can add our other positions. And so, oops, sorry. If we go to our tool and we want to go to position 2, which is going to be this fastener here, we can just put the tool here, and I can add a position, and then I apply that location. Now I can go to the next one and apply that location, and the next one, and apply it, and go to our next one, and the next one, and our final one. Okay, so we have those positions programmed in here, but now we can go ahead and we can assign those tightening sequences to our image. And if we go up here to position 2, let's select that, and we can tell that this is position 2. Now we can just simply tap and we can put that where we want here, or we can get a little bit closer with some of the other items, but let's just turn on all the rest of these real quick. And go to position 2 and go to 3. Oh, I think we put 3 up here. And 4. And 5. And 6. Or did we go? Sorry. 6 is here. 7 is here. And final position 8 here. All right. So if we like that, we can go ahead and we can save that step. And that would be using preset 1 on our system here. So let's go ahead and make sure that we have all of that. In our tightening job here is where we can tell which preset on our DC tool we like the system to use. And then we can also, if there is an error, which retightening job we would like to use. And so we can go through these real quick and enter that. And our last one. And perfect. Now we saved that. Now though, all of those will use fastening preset number 1. And what that fastening is it's basically going to run down our fasteners 4,000 degrees of rotation. So this could be an example of if we are compressing a gasket and we want to have those fasteners run down all to the same height in compressing that gasket. And now we want to add another fastening step that will be the final torque for that, and that can use preset 2. So what we can do, since we already have the fastening data and everything saved, we can just copy that step. Now we can go in and edit it, and then we're going to change our tightening job to 2. And we'll just go through and do that for each one. And with the retightening, we do have the option to allow the operator to attempt that retightening up to 9 times, or you can have that attempted anywhere from 0 to 9, whatever you would like for the retightening job. And so that one is done. We can save that. And let's go ahead and save the whole program now. And now we can go ahead and load that and run it. And so right here, you can see it's giving us our target of our first fastener on our thread block. The tool is currently locked and there is no power to the tool. So if I try to run the tool, we're not getting any power until I get to the correct fastener. And so you can see that the indication changes from or to a green value, and we can go ahead and run this, and we get a good signal back from the tool. Again, we're simply just running this down 4,000 degrees of rotation. And so if we were to get an error, I am sorry, this is an angle step, so Now it has changed to preset 2 here, and the tool is locked again until we get to the correct fastener. It will then, our target torque is 2.75 inch ounces. And so with this fastener, what I was trying to demonstrate was the ability for an error to be produced. And so if we do this and we just let the fastener run or the tool run, we're going to get a timed out error, or it could be an angle error. And so in this case, we did get the error. The system has alerted us, and it then did not count this particular fastener. So we still have fastener, or we still have the additional remaining fasteners that weren't counted. It's still telling us that we need to be here. So I'll go ahead and we can run this down to get our good signal. And this will then again move that. And then the system will go ahead and reset itself if we want it to, or we could wait for another part to come in to do that same type of setup. So this is how we can or not kind of, but how we can control the operator and move them through the sequence because, again, there's power to the tool only when we are in the correct location. As you can see here, that the tool is in an okay position. If we move outside of that, it immediately locks it. So there is not the ability for the operator to do any other fastener but this particular one within that program. Again, there are other things that the touch itself can display. There can be messages that say that you're going to add this particular component to the unit, then that can be brought up as a message. We can have connections through input and output devices, whether those are thumb switches, to make sure that the part is correctly locked. A lot of that can all be controlled through the DPC touch. But as it relates to sequencing, this is how that particular item functions. So with that, that's going to conclude today's webinar, and we'll go ahead and move on to our questions and answer section. And so today, Chris, do we have any questions?
Hello, Dave. One of the first questions we had is, can an air tool be used with this positioning system that you demonstrated?
So the system does allow for the use of an air tool, but there are some parameters that the tool needs to have. It needs to be able to have air ports on that so that the system can generate basic time signature for the tool when it's on and then when it's off. And so instead of relying on a DC control tool to be able to provide, if it was a good rundown, it uses a time-based signature. So it can be used with an air tool. It could also be used with a standard electric clutch tool. That would, again, work the same way, where we develop a time signature for that fastening process. And if it's outside of that window, then it will generate an error. So yes.
All right, thanks, Dave. Another question we had is, can a barcode system be connected to this system you were demonstrating?
So a barcode scanner can be connected to the DPC Touch, and it can pull up a specific program based off of the part that is being used. And that barcode scan can be something that is on the workstation. The operator could scan for that part, or it could be a situation where the operator would scan the actual part. And as long as there are some standard identifiers within that, we can tell the system just read those particular identifiers. So if there is a serial number that's part of that code, but it's always the last 5 digits, we can tell the barcode just read the first 10 digits and don't read the last 5 digits. And it will use that particular barcode for the particular program that needs to be selected. So yes.
All right, Dave. Another question we had is, can the torque values be pulled or stored from the process?
The torque values would be stored within the DC tool that would be used. So the information that we can send out from the touch would be a batch complete signal or a fasten OK signal. But to get the torque data, that would come from the tool itself.
All right. Another question is, can this be integrated with the PLC system?
It certainly can. We can use that the PLC again to pull a specific program that needs to be uploaded. It can be used in conjunction with different inputs and outputs. So yes, a PLC definitely can be integrated with this system.
All right, Dave. I think that's all the questions we have for today.
All right. I want to say thank you very much for joining us this month. We look forward to seeing you again next month in our next webinar. So with that, have a good day and we'll see you next time.